Hello, dear students. Welcome to this session. So, in previous session, we have discussed about type 1 problems on journal bearing. So, what is the type 1 problem? Where the diameter of the journal or the shaft that is known. And there are some specific things that will be asked, and only those things that we have to calculate, not complete design. So complete design that is related to the type 2 case where the machinery will be given along with the bearing or the journal bearing which is used for a particular kind of machinery. Say for example, centrifugal pump, reciprocating pump, or a steam turbine, or a IC engine. So like that, the specific type of machinery will be given, and based upon that machinery, we have to note down the recommended values, and then we have to proceed with the general procedure. But in this case, type 1 problem, so diameter will be known. So some of the specific things that are to be calculated. So take the example of take one more numerical problem which is asked in one of the previous question papers, VTU question paper. Say the problem statement is like this: 75 long journal bearing and having a diameter of 75 So here you can see that length of the bearing as well as length of the diameter of the shaft or the journal both are having the equal values. So hence this kind of bearing we can say it as a square bearing, and it supports a radial load, not axial load. Radial load of 12 kilonewton, 12 kilonewton, and a shaft speed of 1800 rpm. 12 kilonewton is W, and capital N is 1800 rpm. And here the ratio of diameter to the diameter clearance is given as 1000, and viscosity of the oil is zero point zero 0.01 pascal second. That is what we are representing, or we are indicating notation here as capital Z. That is absolute viscosity. And operating temperature, that is not given. After that, determine what to determine. The first one is Sommerfeld number, and the next one is coefficient of friction, that is based upon the Mackey's equation. Suppose if the bearing is lightly loaded means, then we have to use the Petrov's equation. Now here there is nothing is specified about the lightly loaded or heavily loaded, so we have to assume that the given bearing is heavily loaded, even though the Mackey's equation is to be used, that is specifically mentioned here, so we have to use the same equation. After that, the amount of heat generated, that is Hg, there is also question mark, and then the power lost due to friction. So these are the things that are asked here, and with respect to the given thing, so we have to manipulate, or we have to simplify, or we have to calculate some of the important things such as diameter clearance. So the ratio of D to CD is given. So take this CD to the LHS. So that D by 1000 is equal to CD. That is nothing but a 0.075 That is the diameter clearance. Hence, we can calculate the radial clearance, which is half of the diameter clearance, CD by 2. So that value is equal to 0.075 divided by 2. So that is 0.0375 And also we require in some of the steps the RPS value. RPM value is given here, capital N. So small n is RPS. So that is capital N divided by 60. That is 30 RPS, revolutions per second. And another thing that we have to carry out here is to calculate the pressure. So bearing pressure, or pressure is given by W divided by L into D, or W divided by 2RL. 2R is nothing but capital D itself. So no need to use the data and equation for this. You can remember this equation, W divided by L into D. So by using the ratio, you can get the value of pressure 2.133 Newton per mm square. And also we can get the value of radius of the bearing, as diameter is given half of the diameter, that is 37.5 mm. So the first step that we have to calculate here is the Sommerfeld number. So we have to assume that there is no side leakage. So there are two equations, they are there in the data handbook in page number 354, 15.6a and 15.6b. So 15.6a refers to the equation of Sommerfeld number without side leakage. Usually what we are assuming without side leakage itself. So 15.6b, that is related to the with side leakage. So these are the different cases related to the calculation of Sommerfeld number. So use the first case. So here what we get, the value of S as 8.439 S divided by minute. So you can convert this one into per second also. So divide this one by 60, though that you will be getting the value in per second. So this is what the value that is required, 8.439. So here the value of R by C, R is 37.5 mm and C is 0.0375 uh, mm, and that is whole square, and Z is 0.01 Pascal second, capital N is 1800 rpm, and next one is pressure P 2.133 Newton per mm square, and 10 raised to minus 6 is the conversion factor for the Newton per mm square into Newton per meter square. And next that we are getting the value of S, Sommerfeld number. Next thing that we have to go for the calculation of coefficient of friction. So coefficient of friction based upon the Mackey's equation that is available in data handbook page number 353, equation number 15.4b. So by using this equation, say F is equal to Ka into Zn by P into R by C into 10 raised to minus 10 plus delta F. So there are some of the constant terms, say Ka. Ka is given by 0.195 into 10 raised to 6. And this value is to be used whenever the full bearing that is given, that is beta is equal to 360 degrees. Suppose partial bearing is given, means in that case beta value is other than 360 degree. So that value is to be used with the equation which is there just above the equation of Ka. Now Ka is 0.195 into 10 raised to 6 since beta value is 360 degrees, and delta F is 0.002, and this value holds good when the ratio of L by D is in between 0.75 to 2.38, 2.3 or 38. So up to this you can use the value of delta F as 0.002, that is constant. Suppose if it is other than this range, means in that case we have to use the different value. So now the value of L by D is equal to 1. So therefore we can use this as the value for delta F. And after this substitute all the values in the respective equation, so that we will be getting the value of coefficient of friction F, 0.195 into 10 raised to 6, 0.01 into 30 divided by 2.133, that is pressure, and this is Z, and this is small n rps, and this value is R, and this is C, and these are the constant values, so that the value of F is 0.004743, that is the coefficient of friction. So now by using this coefficient of friction, we can calculate the heat generated and power loss. Power loss is nothing but the amount of heat generated during the functioning or due to friction. So heat generated is given by F into W into V. F is coefficient of friction, W is radial load, and V is velocity. Available in data handbook page number 360, equation number 15.11a. 15.11a. So Hg is equal to 0.004743, that is small f, and 12 is the radial load, 12 into 10 raised to 3 newtons, and the velocity is 7.068, that is calculated here. V equal to pi dn by 60 into 1000. Pi is constant, d is 75 mm, n is 1800 rpm. So after substituting, what we get, the value of V as 7.068 meter per second. So the value of Hg, heat generated, is equal to 402.3 joules per second or watts. Joules per second or watts. So Hg value is equal to 402.3 joules per second. And the next one that we have to calculate is the equation or the value of power loss due to friction. So if you divide the given value of or calculated value of heat generated by 1000, so the answer what we get is power loss, that is in kilowatts. So this value is divided by 1000, so that the value of power is 0.4023 kilowatts. So this is These are the things which are asked in the problem statement. So what we have calculated. So the next we will take one more problem. Say this is also asked in one of the previous year question papers. So here we have to calculate power loss itself. So if you see all the questions from related to this first kind of problem, either you will be asked to calculate the coefficient of friction or heat generated, heat dissipated, whether the artificial cooling is required or not. And also uh, some of the cases you will be asked to calculate only power loss. So here power loss for a Petrov's bearing. Petrov's bearing is nothing but lightly loaded bearing having a diameter of 100 mm and a length of 150 mm. So length is more than diameter here, so it is a long bearing. And radial clearance of 0.05 mm. Speed of the journal is 1000 rpm, and the lubricating oil is given here. Say name of the oil, that is SAE 10, and bearing operating temperature is 60 degrees centigrade. So this is what a little bit different here. So instead of giving the viscosity value, he has in this problem the name of the oil is given. So with this name of the oil, we have to get the value of viscosity first. So that is what the different problem with respect to previous problems. So diameter of the journal D is equal to 100 mm, length of the bearing is 150 mm, C radial clearance is 0.05 mm as given, and RPM is 1000 RPM. And we can note one more thing here, that is oil name is SAE 10 and operating temperature is 60 degrees centigrade. Radius of the journal, that becomes 50 mm, 100 divided by 2, and speed of the journal in per second is rpm by 60, that is 16.67 rps. So the first step that we have to carry out here is we should know the value of absolute viscosity. So since the absolute viscosity is not given, so instead of that name of the oil is given, so we have to refer the table number 15.1 of the data handbook, page number 363. So name of the SAE 10. So this SAE 10 oil refers to the line B or curve B. So there are a number of curves that are there in figure number 15.3. So with respect to that figure, so B curve that refers to or that is representing SAE 10 oil. And specific gravity of the oil at 15 degrees centigrade. So this is also tabulated in the same table. So this value is 0.8894, that is specific gravity, unitless. And by referring the figure 15.3 and page number 352, so here uh, so by using this figure, we can get the value of ZK. So figure number 15.3 with respect to operating temperature, which is there at the top abscissa, and on the right ordinate y-axis, the ZK value, that is kinematic viscosity in centistoke, that are listed. Now, with respect to 60 degree centigrade and curve B, so ZK value that is obtained here is 17 CST, 17 centistoke, 17 centistoke with respect to operating temperature here, and name of the curve. There are number of curves A, B, C, D, E, F, G like that. So for the B curve, the value of ZK is 17 CST, 17 centistoke. So this centistoke is to be converted into meter square per second. So this is to be multiplied by 10 raised to minus 6. 10 raised to minus 6 meter square per second. So equivalent value of CST in meter square per second is by multiplying 10 raised to minus 6 to the obtained value. So this is kinematic viscosity. But actually we require the absolute viscosity. So absolute viscosity is defined as the ratio of absolute sorry, kinematic viscosity is defined as the ratio of absolute viscosity to the mass density, absolute viscosity to the mass density. But here the specific gravity value is obtained. So with the help of that specific gravity, we have to get the mass density. So before proceeding with the calculation part, say Zk is given by Z by rho. That is, Z is absolute viscosity divided by mass density. And Rho is the specific gravity at 60 degrees centigrade or operating temperature. What is given here, that is 60 degree. So this is the equation which is there in the data handbook. So by using the same equation that is available in page number 352, uh, so specific gravity at 60 degree operating temperature that we have to calculate. So rho 15, that is specific gravity at 15 degrees centigrade, and that value is noted in the from the table number 15.1. That value is 0.8894. This is what specific gravity minus 0.00063 into bracket T naught. T naught be the operating temperature, that is 60 degrees centigrade, minus 15. And this is available in data handbook page number 350, equation number 15.1 F. So by substituting all the values, what we get, the rho value as 0.8610. 0.8610, this is unitless, dimensionless quantity. So specific gravity is defined as how this particular value is defined, or the notation specific gravity is defined. So specific gravity is defined as the ratio of mass density or weight density of the oil to the ratio, that is divided by mass density or weight density of the water or standard fluid. Standard fluid for this oil is water. So if we want the value of mass density of the oil which is given here, or say 10, so this value is to be multiplied by the mass density or the weight density of the standard fluid, which is water. Of water is to be multiplied. So 0.8610 multiplied by 1000, that is what the mass density. Now we want the absolute viscosity value. Absolute viscosity is given by kinematic viscosity multiplied by the mass density. So mass density or weight density we can say. So weight density is given by rho, that is the specific gravity, multiplied by 1000, multiplied by 1000. So in the general design procedure it is written divided by 10 raised to minus 3. So both are same things. Say if it is written to zk divided by zk into rho divided by 10 raised to minus 3, instead of writing into 10 raised to plus 3, both are same itself. So and then what we get, the value of z in Pascal second, that is Newton second per meter square, as 0.01464 Newton second per meter square. So this is what the procedure to get the value of absolute viscosity. How to get absolute viscosity with the known value of oil? First of all, we have to know the name of the curve available in the figure from table number 15.1. Also we have to note the specific gravity value at 15 degrees centigrade. Next we have to refer figure number 15.3, page number 352, and operating temperature is 60 degrees centigrade, and with respect to curve B, we will be getting the value of zk, that is kinematic viscosity in centistoke, that is 17 centistoke here, and that is to be converted into meter square per second by multiplying 10 raised to minus 6 to the obtained value. Then we have to convert this zk to z. So to get that value of z, we have to use zk into specific gravity multiplied by 1000. So specific gravity at a 60 degree operating temperature, so this is available, or this is to be obtained by using this equation 15.1 F, page number 350. So that the value of z is obtained as Pascal second. So the next thing that we have to go for the calculation of coefficient of friction. So why this coefficient of friction is required here? Power loss is to be calculated. So there the value of F is essential. Since the Petrov's bearing is given, so we have to use the Petrov's equation 15.4a, page number 353. So in this equation, 2 pi square into 10 raised to minus 6, Z is absolute viscosity calculated, and R by N is RPS 16.667, and pressure P, that is unknown. So we have to calculate it, and that value is W divided by L into D. W is not given, so L and D they are known. Substitute as it is. Say W divided by L into D here in the place of P, and 50 is radius and C is radial clearance. So what I get, the value of coefficient of friction is 72.26 divided by P. sorry, W, that is load, radial load, which is not given in the in this problem. So now substitute the value of F in the equation of power loss, that is FW into V divided by 1000. V is pi dn by 60 into 1000, so V is equal to 5.24 meter per second. So PF is 72.26 divided by W, that is coefficient of friction. W, that is unknown, keep it as it is. 5.24, that is the velocity, divided by 1000. So since W is unknown, W divided by W is gets cancelled here. So the value of power lost due to friction is 0.378 kilowatt. So this is what the required answer. So this is about the type 1 problems. So I hope you have followed the steps. So in the next session, I will take some more problems or application type problems. Thank you.